Okay, guys. As you can see, we continue in chapter 11, and then I think when we finish chapter 11 and 12, 10, we'll do all these 4 quizzes. We have a 3 chapter wise, so after finishing 3 chapters, we will have a quiz and exam. So nomenclature. So with the nomenclature in mind, we are using the real chemistry or chemical nomenclature, meaning naming of the organic compound, using the IUPAC system. The IUPAC is, as you can see, is abbreviation for International Union of Pure and Applied Chemistry. This association started after World War II, I think in France, and they start naming those naming of the compound, and this will be universal. So you go anywhere on this globe, in this earth, you will have the same nomenclature, the same name of the structure. So to minimize or to just eliminate any confusion about the name. Now we do have commercial names, correct? And we do have commercial names, and we have common names, correct? Just to let you know that, but our names, the real chemistry names we are going from is IUPAC name. That's the true name of any organic structure. Everybody's following? Just an example for you here. I have here, this is a condensed structure of a compound. The IUPAC name will be, this is carboxylic acid, correct? This is functional group of carboxylic acid. So therefore, IUPAC will tell you have to count number of carbon, 1 and 2, this is eth, correct? And then you have ethanoic ethane, so ethanoic acid. The ic acid is the IUPAC naming for the carboxylic acid, ethanoic acid. This is the IUPAC name structure. However, we have a common name. You will see that's typical for the organic compounds, not the inorganic compounds. Other chemicals not, just specific organic. Common name called acetic acid. Common name called what? That's a common name here called acetic acid. Now we have sometimes commercial name, wait, somebody will tell me. Somebody knows what's the commercial name of acetic acid? What's that? Correct. Thank you very much. You made my day with it today. So vinegar. So you will see in the organic chemistry, we have 3 names to name this compound. The common name, the commercial name, which is found on the shelf, on the stores, and then the IUPAC name. But our goal is this one here. I mean, it will be nice, it's a plus to know the commercial name and the common name, but not always we'll be able to figure out a common name or a commercial name unless we go to textbooks or to the reference and look at the literature, common names, what's inside the literature. But that's vinegar is understood, common name acetic acid, but the IUPAC name is because we have a functional group of carboxylic acid, number of carbons is ethane, alkanes, one single bond here, ethane, and then take the E out of the ethane, so you go from the ethane as skeleton here, take the E out of the ethane, and then you see oic acid. Oic acid. So let's me here, not ic acid, but ic acid, that's organic, but you will add oic acid. So you take the E of the alkanes, and then you add oic acid. That's an example of the nomenclature. Any question, guys? Any question? Don't be shy. If you have any question back there, just let me know. I will be doing my best to explain things. But that's always the case. Most of the organic compounds, they have three names. The real name, the real IUPAC name, that's the real chemistry name, the real chemical. And then you have a common name, correct? And then you have a commercial name that you can find it on the shelf. I'll come back to you. Just an example here. That's inorganic now. Even on inorganic compounds, they have a name of this. What we call this? It has IUPAC name. IUPAC is not for organic, for all the chemicals, whether inorganic or organic. But most of the time we see the IUPAC name is used for organic, but we use it for inorganic. What we call this compound? This is an inorganic. This one is inorganic. So what's the name of it? IUPAC name. Sodium what? Sodium hydrogen carbonate. So this is sodium hydrogen carbonate, correct? That is the IUPAC name for this. So this is the real name according to the IUPAC name. But do we have a common name for this and commercial name? What's the common name? Somebody will tell me? I'll come back to your question. Just hold on. What's the commercial name of this? Sodium. That's not a commercial name. That's a common name. Bicarbonate. That's a common name. Your answer is the commercial name. That's a common. The commercial name will be what? You told me the answer. Yes. The commercial name called baking soda you are using for cooking. Cooking cakes, whatever, the dough with the flour, to make the flour going up. So that's a common name. Baking soda here, to bake. Baking soda is what? The commercial name. That's you can find. Commercial name means you find it on the shelf in the stores, at the stores. So this is just an inorganic. So IUPAC is not only organic. It can be. This is an union, association, to naming compounds. Okay, guys. So now I'm back to you. What's your question?
Do you want us to know all the names for the quiz or the exam, like the commercial name, common name, the commercial name?
No. More all the questions in the final exam and the quizzes will really depend on IUPAC name. What's happened is in the IUPAC name, you do have system to follow. You see, this is 2 carbons, F, from ethane. So that's an ethane. Then you have carboxylic group. The carboxylic acid will have OIC, oic acid. So we're not, by all means, going after common or commercial. We are just concentrating all quizzes, exams, and the final exam only on IUPAC naming. That's the real chemical name. Everybody is following? Any question, guys? Any question? Okay, so can I take this one out? Take this one out. And don't come to the idea just IUPAC, it's just for organic. No, it's a union, it's an association for pure substances, for pure chemicals. Okay? So let me take this one out, and then we'll go further from there. isomers, we talked about the isomers in the last topic, in the same chapter. We said isomers, typical organic compounds, they share a lot of things in common. Some of those, what you can see as they have the same molar mass, the same molecular formula. So molecular formula means this is molar mass. So if you calculate the molar mass for each isomer, you will see of a compound, you will see them the same, because you don't add any other atoms to them. They are 100% identical. So they have identical in the molar mass, number of atoms there, correct? So what are the other things? They have the same number of and types of atoms. There's no change. The only change of the isomers means they are having the opportunity to rotate if they have single bond. The rotation will leave those some of the substituents or some of the group attached at different space. So they will not share the same space. For example, one group, one substituent, one functional group will be towards you, the other one in the back of the molecule, correct? If you have a mirror. Or one will be at the top of the molecule is in the plane. One will be sticking in the top, one will be sticking at the bottom. Are you following me here? That's the arrangement in space, arrangement of atom we have to write in space. That's lead to the isomers. However, they share the same molar mass, so same and same atoms. And same number, this is type or kind, or type. The same type of atoms, same number of atoms. So that's the share. The only thing, that's the only difference here. Their location in space is totally different. They can stick out of the molecule if the molecule is a planar in the plane, or they can go in the back of the molecule, or they can stick out at the top of the molecule or the bottom of the molecule. So I think we covered this one here, and we can look into the different types. So substitute. It says draw all isomers of what we call this compound. Somebody will name this compound C5H12. You look at the alkanes. The alkanes general rule is CnH2n plus 2. That's for the hydrocarbon alkanes. Now let's see if we have N is 5 here. Correct? So C5H2 multiplied by 5 plus 2. So this one here, C5H12. This is an alkane, so this is an alkane. We know this is an alkane, correct? And this alkane will be, because it's 5 is pent. That's from Latin, or the Greek first Greek and then Latin came later on. So bent, and alkane always ending with ane. So bentane. So the ending, so this is pentane. 5 atoms of carbon, that's pentane. Correct? So you can do a lot of isomers. I'll leave it up to you. Practice, and you have any question. So first of all, the easiest one is you just put all those 5 together. Correct? Then say, well, this is like CH3, CH2. I'm writing the condensed structure here, not the expanded one, the condensed one. So then I say to myself, how about taking one methyl group and let it stick out or in or out the plane of the molecule of this pentane? Well, I can do that, yes. So suppose I will take this one here, sticking it at the third one. So it's always trial and error to see how many isomers you will have. So I can do 1, 2, 3, 4, and one will stick here. That's another. I took this methyl here, and then let it stick on number. That's 1, 2, 3, 4. This is no longer pentane. The long chain is butane, 4. And this sticking here in the second will be 2-methyl butane. So the name of this isomer is 2-methyl butane. But the same number of carbon, the same number of hydrogen, the same molar mass, correct? No change. The molar mass is the same thing, C5H12, correct? Now, can I do another one? Yes, I can do another one. How about if I do this one here instead of butane? How about do here 4 and then 4 and then here? That's still 5, correct? Everybody agrees? That's still 5. And the skeleton here, the main skeleton is propane, 3, propane. But then I have the propane from one side of that. 1, 2, correct? So this is 1, 2 dimethyl, because you have 2 methyl group, dimethyl propane. So this is, so we made out of pentane an isomer called methyl butane, 4 carbon, and we made out of this 1, 2 dimethyl propane. So we made the propane, 3 carbon skeleton. We made the 4 butane, 4 carbon skeleton, and the main one is 5 of them together. That's the C5. That's the major one. Are you following me here? Everybody is following? Can we make it further? Yes. You can hook up at the first one, and now I have the 2 metals here. I can hook up those methyl group, the 2 ones here, this and this one here. I can hook them up instead of 1 carbon 2. I can hook them on this carbon what? 2 will be isopropyl, correct? Or 1, 1 dimethyl, correct? Pentane. So you can always try this in your pace. So it's the Chem 101 will help you a lot with this. So I can another possibility. I can make here 1, 2, 3. Now instead of 1 here, I can hook those here. This is H, this is H2, this is H3. Now this is 1, dimethyl pentane. There's still 3 carbons, the skeleton, the main skeleton, 3 carbons. But now that the 2 methyl group attach not to the second carbon, but to the first one, correct? So that's so how many we got now? 1, 2, 3, 4. So you might sit down with yourself and try to play around this methyl group, moving it back and forth. Can I have another one? Yes, I can. I can put dangling those 2 sides methyl. I can want 2 sides methyl. Correct? Everybody's following? I can do that. So, but anyway, so you can try it at home. Usually, it's not the final exam question. Might be exam or quiz because I give you more time. But those type of isomers needs time, and I don't think so. Will give you a very difficult compound because it takes a lot. You see here, it takes about 4 or 5 isomers. Then you have to draw them by yourself and confirm them. So those type of questions will not. I don't think so covered in the final exam, correct? Because they take time to just trial and error if that's correct molecule or not. So. Substituents, we said anytime we have a functional group that's attached to the main skeleton, to the backbone of the chain of the molecule, we call them substituent. We call them what? Substituent. Or groups, attached groups. And sometimes they are really, in a way, they are branched. They can't come in between, except for the imides. That's a little bit different. But most of these substituents or groups, attached groups, they come in a branch way. So in order to get this one here figured out, whoops, sorry. In order to get this one here, straighten up, oops, why is it not working? So this is, yeah. In order to get this one here straighten up, you will have to know, because this way of writing, I don't know where is bromine is attached to. So it's not a condensed, correct, by all means. The condensed has to show at least a single bond between the carbons. But when I write it in the condensed way, I will have more. This is just like a molecular formula type of writing a molecule. But the best thing here to have it, CH3, a condensed way is very good. But the best is expanded formula. Expanded formula, you have all the bonds are appearing to you, and you will know where those substituents or branch groups are attached to. So I have a CH3, starting from here, CH, correct? And then I have here Cl, that's all is condensed. Then I have CH2, CH, and I have Br, then I have CH2, CH3. Okay, guys? Now, if you look at this, the first thing to name those type of compounds, whether they are alkanes, alkynes, in general, the hydrocarbons, I look at the number of the longest chain. So look at the longest, what we said, longest chain. Here's the longest chain. To me, looks like this is the longest chain. Okay, so that's number one. Number two, I have to look at the substituents alphabets. Chloro start with C. That's chloro. With the C. Bromo start with the what? Let's write it small b, not capital. Just here, just to show you here. Bromo, correct? This is a B. Now, which will come first in alphabets? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, and so on. So which one will come? B or C? A B. So we have to bring this one here first. Okay, so number two, you have to look at the alphabets priority, priority. The alphabet's priority means the alphabet will come, whatever is the setup or the arrangement, the order of those alphabets. A will come before the B will come before the C, C will come before D, and so on. So then the longest chain is 1. So I have to start with what? With the bromo comes before. So I'll start from here. 1, 2, 3, 4, 5, 6. I don't agree with the name there. So they put bromo at 4. No, bromo has to be what? Where is it? 3. That's the reason I can't tell about this. Let me take this one here. Yes. So here it is. They said 2-chloro. The C, however, comes after the B. So you start with, so the naming of this, I will not agree on this, because why? Why we don't agree? Because the B has to come before, and they have it. But the number 4 for the bromo is not correct. Yes?
I think you missed the CH2.
What's that?
You missed the CH2.
I missed what?
There's 2 CH2s, 3 and 1.
Oh, it's connected to the 4th? Did I miss the one of the carbons?
Yeah,
the right side. So 1, 2, 3. And it's attached to the 4, then it's correct. It's attached to the 4 then, correct? So let's see. So 1, 2, 3, 4, 5, 6, 7. So how much we have here? 1, 2, 3, 4, 5, 6. Yeah, we are missing. You are correct. So we are missing 1 carbon. I apologize. So we have, then will be H, and then we'll have to add, this is CH2, CH2, and CH3. So now we have 7, correct? Heptane. Heptane. 7 is hep. So number 3 is connected to the chloro here. And number 4, or the 1, 2, 3, 4, that's the bromo here. And number 3, yeah. We have to, yes, so here it is. That's ours. So number 3 then, this is 4, correct? And then they said number 3, correct? Where does that give the chloro? They give the chloro here, number 2. But still I don't agree with that. As I say, whenever you see the alphabet is very, very crucial. After the long chain number, you have to number you look at the alphabet. Bromo will come before, correct? Bromo at 4, correct? So this is 4 bromo, but not 2 chloro. The C has to come, has to come after the bromo itself. So it will be 4 bromo. Let me see. We said 4 bromo, 6 chloro, and heptane, correct? Now, if you look at this way here, will be 1, 2, 3, 4 bromo, still 4 bromo, correct? Either way is 4, 5, 6, 7. 4 bromo. We have to look into this. This is very good example. 4 bromo, and then we have 2. You can do the numbering from left to right, or from right to left. So now let's see. 2 chloro heptane. Now which one is correct? Which one is this or is this? Now I did the mistake here because we have always to yield after putting all this both has to yield lowest numbering. Yields lowest numbering of the substituents. So now we have 4 bromo in both, so that's good. 4, 4. However, here we have 2 chloro and we have 6 chloro. Are you following me here? So which one is lower? 4-2 or 4-6? 4-2. That's correct. Then theirs is correct. Theirs is correct. The PowerPoint numbering is correct. So we have to have 2 things together. First, the longest chain number, then the alphabet number, and then you look at the whole thing has to yield the lowest numbering. 4-2, 4-3. And you don't go for 6 or 4-8 or whatever the number is. Always you take the lowest numbering. The lowest what? Numbering. So theirs is correct. So what's the condensed structure for bromo, 4 chloro, 2 methylhexane? So what's the backbone of this? I will leave it to you. You can do it. What's the backbone of this? Hexane. How many carbons? 6 carbons, correct. And you have to look into the alphabet. The bromo will come before. See, that's 4 chloro, yeah. Yeah, 4 chloro. The C will come before the M. Can you see that? The C will come before the M. And then after you have determined the longest chain, you have determined the alphabets of the substituents, priority. Then you have to combine the numbering. Which one of the two possibilities reading? From left to right or to right to left? Which one will yield to you the lowest numbering ever? Correct? So whether it is 4 to 2 or 4 to 6, whatever that really is. Are you following me here? So those three items, guys. Longest chain, priority of alphabets, and then both combination has to yield the lowest numbering ever. Correct? If you have larger number, that's not correct, according to the IUPAC rules. So, cyclic hydrocarbons. Well, cyclic hydrocarbons, I'll give you the examples here. Cyclic hydrocarbons, they connect themselves in a ring. Okay, this ring can have no double bond. All of those are single bonds, or they can have one single bond or two single bonds. But this cyclic hydrocarbons, they cannot have three double bonds. That will be what? Aromatic then. The compounds we call aromatic. The basic structure of it, benzene, correct? So cycloalkanes means what? You have single bonds. So the cycloalkanes here is all of it. It is means all those are alkanes, meaning single bond or single bonds. Now you can see those how they structure, they connected, all the carbons connected to each other in a cyclic way. They are close to each other, closing each other bonds. So we have the 3-1 is called, always give the abbreviation called cyclo at the beginning. Cyclo, and then number of carbons plus number of carbons. So then if you have, then you have what? The single bond is ane, the double bond, the single bond. The double bond, the double bonds called whatever that will be E and E at the end. So E and E at the end. Correct? So for example, I have here the nice structure. So I decided to have, you know, that's all those are what? Condensed. Correct? Not expanded. But I can sometimes write them in the way for molecular formula. I'll just put this one here, like this. So this one here, like this. Okay, looks like square because the single bonds are equal in length. So square looks like square. Correct? If I have to open all this, you know, hydrogen, the hydrogens, correct, then will be expanded one. That's the expanded one when you open all the hydrogen bonds. But this is for the molecular formula, you know that this is CH2 here attached. So this is CH2 attached. So this is cyclobutane. This is what? Cyclo, and there's 4 carbon. 1, 2, 3, 4. Butane is an alkane, but the cyclic means all these double bonds are connected. I mean, single bonds are connected to each other. Now I can go from this having something like this. Okay, guys. So what's the name of this will be? Cycloalkenes means cyclobutene. So let me take this one here out. That's 4 carbons. So cyclo, then butene. Now suppose I decide to have, well, how about I can go maximum? Maximum what? Maximum the second one. So that will be cyclobutane, but I have two double bonds. This E and E means double bond. So I'll be what? Diene. But-diene. If I have a 3 ones, because that will violate the octet rule. I can't have for carbon. I can't have a third one. So maximum of 2. Third one, then you have aromatic stuff, aromatic structure. So that will be cyclobutadiene. If one single bond, but-ene. One single bond is ene. If I have 2 single bonds, it will be diene. I can't have a third one because that will violate the carbon has only 4. It can't have 5. Correct? Can't have 5 attached to it. So 4. Now, if I have to have a third double bond, then this compound will be different. It will be what? It will be aromatic, like in the hexane here. So the hexane here, you take all the sum of the hydrogen, you will end up having benzene. So 3 double bonds here. Correct? So this is about the cycloalkanes. Now, the cycloalkanes physical properties and chemical properties totally different from the original they came from. They are alkanes by all means. They are alkanes. However, they are a class by itself, a group or a class by itself. You cannot mix them with the normal alkanes. So their physical and chemical properties are different from whatever they came from. They came from originally from what? From alkanes. However, then they will come and form their own class, their own cycloalkanes. They have something in common with alkanes, like they are not soluble in H2O and similar polarities. But in general, chemically they will behave different from the original they came from. Okay, guys. So shape of alkanes and cycloalkanes. This is the alkanes in general are tetrahedral, correct? Alkanes are always tetrahedral because they have a single bond. So single bond are always carbons here and all these hydrogens, for example, just carbon and hydrogens. Carbon and hydrogens, carbon and hydrogens, carbon and hydrogens. So anyway, so tetrahedral all the time. The single bond alkanes are tetrahedral, correct? The cyclo, however, they have like a very unique cyclic structure, like a cyclohexane, for example. This is the cyclohexane without single bond, without any double bond inside. Okay, that's a molecular formula type of drawing, correct? And the condense you will have, then you have to put CH2, that's a condense, CH2 and so on, CH2, that's a condensed one. And the expanded, then you have to really take the hydrogen here, say, okay, the hydrogen is here, and then take this one here out and so on. So if you take hydrogen out, take this one out, let it stick. Here it is. Take this hydrogen out, and you have, and then take this one out, sticking, take this one out, sticking out. This is the expanded one. The condensed, you don't show the carbon-hydrogen single bond. The expanded, you show all type of bonding. This is cyclohexane. Cyclohexane, the unique about it, it came like looks like similar to a sofa, you know. It's not really a chair per se. It looks like a sofa because it's expanded through the molecule, and you can see, looks like this. This to me is more or less sofa than a chair, but we call it a chair type of geometry, a chair type or a sofa type of geometry, correct? So that's, those cycloalkanes are coming, especially the one like this, cyclohexane, has a sofa or chair type of geometry. Now, sometimes it's very hard, like a cyclobutane, it's all this like square here, all of the square, equal length. Now, in this case, it's just what? A plane. So like a flat something, like a piece of paper, correct? Cyclobutane, for example. That's a flat, like a flat plane. So the geometry of it, just a flat plane, it's like a piece of paper. But cyclohexane, because it has more carbons, so you will see some of them sticking up, some sticking down, and it looks like really like a sofa type of geometry. But the alkanes in general, they look like tetrahedral. So if you look at the tetrahedral, an example will be the pyramids of the Incas in Peru and the pharaohs in Egypt. So the Incas and the pharaohs, they have built thousands of years back in history, those type of pyramids, correct? And the Incas and the pharaohs, they have the structure of those pyramids tetrahedral. They have tetrahedral structure. That's when you come to the idea how the tetrahedral, and that is really tetrahedral close to the pyramid to visualize it as a pyramid, correct? And other thing to visualize the tetrahedral is you have two tetrahedrals together. Diamonds. Somebody has seen the diamonds, the big ones, the big diamonds. That's two tetrahedrals together combined. So they have what? Another one like here, and then you have something like this. So you have they share one base, and that look like real. The whole thing looks like a diamond somehow. But anyway, so somebody will tell me why it's very important, the geometry of a molecule. Did you study VSEPR long time ago? Shape and molecule, why it's very important, those isomers, to know about them. Why it's very important? Somebody will tell me? That's especially very important in two areas. Purification of tap water. If you have lakes, if you have rivers, if you have ponds, you need to get rid of all the type of junky stuff, bacteria, viruses you don't see with your eye. The thing you can see in the eye, rocks, shrubs, piece of woods coming into those ponds and lakes and rivers. But we don't see in your eye is the viruses there. And that's what we have. With the help of the geometry of a molecule, we can design a molecule to really trap those viruses and bacteria, whatever, into its geometry, and they will be trapped in and then swept out of those ponds, rivers, and lakes. That's one. The second one is application of those isomers, of those geometries in space, is treating or fighting cancer. Those tumors, you need this chemotherapy. You heard about chemotherapy. Those are using some medications, some chemicals with a specific geometry that's really, they can entrap the tumor, restricting their motion, their movement. So those chemical compounds with specific geometries, they have the ability to restrict the motion. They are really trapping those tumors, correct? And if those chemicals are failing after a while, then the tumor spread out, and then you have the stage of no more tumor, you have a cancer, and that's too late to recover. So the cancer is the last stages of a tumor. So tumor at the beginning of any fractional cells in a body of living creatures, we call it tumor. That's a free radical. So as you can see, the isomers back here, we have two types. I mean, there are other types too, but this conformational isomers. Those isomers coming, they have the ability to move around. They can rotate. They can spin around their axis. So this is what we call this compound. Somebody will tell me what we call this compound. Come on, don't let me down. What we call this compound here, this and this. Come on, guys. What's that? Ethane, correct. That's an ethane. This is a carbon here sticking. In the back of it, there's another one. So this one here, if I write it this way here, that's an expanded one. So now I'm writing this molecule as expanded. Now they have the opportunity to rotate around what? Will be rotation around this single carbon-carbon single bond. The double bond, triple bond, you cannot do that. If you want to start rotating, you break the bond because they are shorter. This single bond, so here it is. Why is this happening? Because single bonds are too long. Compared with single and double, compared with double and triple. Triple even worse. You cannot even move it anywhere. It will break because the distance is so small. You start to, they cannot rotate. They cannot rotate in nature. They cannot. They will be broken. So this is the rotation here on this axis, carbon-carbon single bond axis. That will give you one is up, one is down. If you call this one here 1, 2, 3, and this is 4, 5, 6. So whatever is sticking out will be, this is 1, 2, 3 outside, and then the back 4, 5, and 6. And then you can rotate them out. See, you understand my point? So they are close to each other, but you can rotate them so they spread out. They are farther away from each other. Are you following me here? Everybody's following? Yeah, so that's only possible in single bond. Double bond and triple bond, they don't have the way to do this. Now in the cyclic alkanes, you have you can't cyclic the same way. You cannot rotate the single bond. It will break what? It will break the ring. So rotation is not possible. The same thing with the double bond. Rotation is not possible because you will break the actual what? You will break the actual single bond. However, in the space you can see they can be the groups. They can be together in space, like here the methyl group attached together in the same orientation, and that's we call it cis. They are together. Cis means together. They share the same space together. Opposite to each other, that means trans. Trans means always in organic chemistry and in inorganic chemistry means opposite. Even organic. Some organic crystals, they have trans behavior, so their structure is trans, means they are opposite. Groups are opposite to each other. Are you following me here? So we have, in a cyclic, we have cis and trans. We cannot have conforms here. Conformational isomers or conforms. conforms are compounds that have the ability or for the rotation of the single bond of carbon single bond. The rotation is allowed, is possible, and therefore so the word conform means rotation. Conform means what? Means rotation. Rotational isomers. So their name is rotational isomers too. You'll find them in the literature with the name conforms or rotational or spinning isomers. So they spin, they can rotate. But the cyclic cannot do that. You'll break the structure of the molecule. Double bond cannot do that. Triple bond is the worst, ever worst, because then the whole molecule will just splash all over the space. So you cannot break a triple bond. And it's very hard because you need a lot of energy to break a triple bond compared with the double bond. Single bond is easy to break. Single bond is just, you can see the physical properties, chemical properties. You can burn methane, correct? Natural gas at home, you can burn it easy. You can barbecue with it easy. So, but if you bring any double bond or triple bond compound to burn it, that will take a lot of energy to do. That will take a lot of energy to do, and it takes a long time to get them broken. And you can wait for your barbecue for a long time. So, here it is. Can I take this one out? Everybody has it? Okay, now. Haloalkanes, the word halo means halogens. The halo means what? Whenever you see halo means always means halogens. The halogens here are group 7, group 7A in the old periodic table, or group 17 in the new one. 7A or 17. The 7A and B, those old traditional periodic table, will give you that hint that this group has VE valence electrons is 7 valence electrons. 17 does not give you the whole information about it, but at least you know it has, those are 7, and they are attached to the main skeleton. They are attached to the main skeleton, as here you will see. This is a molecular formula. It's not a condensed, it's not an expanded. So this is not condensed, not expanded. What we call this is a molecular formula. The whole sum of the whole atoms together. But if I want to make a condense out of it, I have to put the carbon-carbon relationship, CH, and then put the Br here, and CH3. That's now what, that's the condensed. If I want to put expanded, then I have to show all the bonding of hydrogen, 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 and then you have here the Br, and then CH, H, H. So this is expanded, guys, and this is condensed, and this is just a molecular formula. This is mostly for molar mass. We use it to calculate number of atoms, atomic masses, to get the molar mass. Correct? So we have 3 types always of structure for the molecule: condensed, expanded. Expanded, you have to show all bonding, and the condensed is just, you have to just show the bonding between carbon-carbon atom. And the molar and the molecular one is just for the molar mass. You just, as you see here, just condense, no bonds. You don't write any bond, just for your calculations. Okay, guys, so I'll go further. As you can see, those here we have those halogens here attached to the main skeleton here. They call it main skeleton or the main chain. Okay, so or the backbone. So you have backbone of the molecule chain, longest chain of the molecule. Okay, all those the same synonyms to each other. So those are attached to the main skeleton here of the compound. And the haloalkanes they have a very important usage. They are used in, you can buy them even out of the, I mean, you can buy them in the pharmacy if you have an injury, and then you can put ice, or sometimes you put some chemicals here, the haloalkanes. They make your stuff, your injury numb, so you don't feel the pain. And the same thing, they are used in medicine as anesthetic, make your body numb, so you don't feel the surgery, the cut on your skin, on your body. You don't feel it because all that area is numb, correct? However, they have a bad application. Haloalkanes go to the air and then attack the ozone. And as you know, if the earth has no ozone, what will happen to us? Can we live in this earth? No. Why? You are right, we cannot live. Why? The UV coming from the UV radiation from the sun, the ozone is protecting us from the UV radiation of the sun. If we have no ozone, guess what? All, including even plants, will be treated for cancer and will die. The cancer will spread out, not tumors, it go cancer. Because this radiation is so energetic, in an amount of energy with them from the sun, they will come and attack our body and then create a lot of tumors, and the whole globe, living creatures will be dying, including even the trees. They will be dead too. And if we lose the trees, we cannot really get amount of oxygen to inhale. So it will be suffocated as well. So you have cancer from one side from this radiation. The other side, you kill the trees, they will be treated. And then if you don't have the cycle of CO2, oxygen, we are inhaling oxygen, getting out CO2. The trees is helping us, taking the CO2, bring us what? The oxygen back, correct? So this is the balance in nature. So those are very, very bad, and I think they try to limit their usage, and this is the bad thing about them. They are very useful. They make your injury numb. You can try them. I think you can buy them from some of them from the counter, I mean in the pharmacy. If you have injury, you put ice, or you put these chemicals on them, and that's fluorocarbons. They really makes you numb. You can't feel nothing. But they can produce a lot of free radicals, which can attack ozone here. So that's just here on the tomatoes. What the structure of the tomato. The structure of the tomato, really, if you look at the tomato, the whole thing, that's the structure of the tomato. Lycopenes. This is a hydrocarbon with at the end what? ENE means alkenes. So this one here, ENE, means now we don't have ANE. ANE, then we have alkanes. Correct, guys? Now we have E here, will be alk, instead of A, will be ENES. Okay, guys? So this is alkenes, and plenty of them. So you can count, I think it's about 13, 14, something like this. You can count those and see how much they are. Okay, guys? So that's in the tomato, that's a hydrocarbon with a double bond. Now, can we rotate this molecule? The answer yes or no? Can we make conforms isomers out of this? Answer is no, because we said that double bond, triple bond, you cannot rotate them. You cannot by all means. You break the whole tomato, you crack the whole tomato, so you cannot. It's the structure of the tomatoes, and you cannot, this molecule, you cannot get it rotate around the axis of the double bond. So this is an example of the double bond. Now we are in alkenes. Alkenes has the structure of, that's the general structure here, guys. And for alkynes, and this is the structure of, general structure of alkenes. Correct, guys? Those are general structure. Memorize them because that will help you a lot whenever it comes to naming. Now, can we get alkanes out of alkenes and alkynes? Alkynes is triple bond. Triple bond. And here we have single bond. Correct? So as we said, no spinning, no rotation around the axis of the double bond or the triple bond. However, we can use a catalyst to change the alkenes and the alkynes, the triple bond, the alkynes ending up here with E-N-E, and here is Y-N-E. And alkanes, bless you, A-N-E, bless you, alkanes. A-N-E, this is E-N-E, and this is Y-N-E, alkynes, pronounced alkynes, correct? So with the help of a catalyst, we can transfer those alkenes and alkynes into alkanes. What we call this type of reaction? Somebody will tell me? It's hydrogen, correct? You let it react with hydrogen, what will be what? Hydrogenation. What we call it? From the word itself, because you are letting it react with hydrogen, this is hydrogenation. That's hydrogenation. Hydrogenation is breaking the double bond and the triple bond into single bond, correct? So, and this one here, all the single bond in alkanes, we call them saturated hydrocarbons. Saturated hydrocarbons. Saturated means hydrocarbons. Means full. The carbon is full in its bonding. Correct? However, those two here, alkenes and alkynes, are unsaturated. Why? Because we can add to them. So here you cannot add. No addition. You can add, no addition. You cannot add to them hydrogen, for example. Here, unsaturated. Why? Because I can add to them. Addition is possible, and that's what we add here, hydrogen. We add here hydrogen. So addition is allowed. So addition is allowed, and this is unsaturated hydrocarbons. Correct? So that's the difference. Alkenes, double bond, alkynes, triple bond, called unsaturated hydrocarbons because you can add to them. You can open up those double bond and the triple bond and add to them. But alkanes, no addition is allowed. You cannot add to it anything. Correct? If you add, that's violation of the octet rule. Carbon is connected. Just maximum bonding on it is 4. You cannot have 5. Okay, guys?
Excuse me?
Yes.
When you say add to it, you add more carbon bonds?
What's that?
When you said add to unsaturated bonds, I mean,
Add to it. You add to it any other molecule. Any other molecule. Hydrogen is a molecule. Correct? So you cannot add to alkanes any other molecule. However, double and triple bond I can add because the double and triple bond opens up, and then they can accept this addition from hydrogen or any other molecule, not only hydrogen. correct? Not only hydrogen, any other molecule. But alkanes, they are really saturated. So, everybody has this? Can I take it out? Let's take this one out.
So,
Yes.
when things are unsaturated, we can add any more?
Yes, that's correct. Anytime you have unsaturation, unsaturation means you have a double or triple bond. You can add to that. Okay. Now, can I go back to this to the tomato, my tomato? Can I change the color of the tomato from red to another color? Yes or no?
No.
Somebody in the back? Yes or no? Yes. Yes. What I will do, you have double bonds. You can add molecules to them, such as hydrogen, chlorine, whatever molecules, bromine, and you will see a change of the color. Tomatoes. Have you seen a purple melon, watermelon? I saw it. Watermelon, purple. Look at this. Google the purple, violet watermelon. So they play with the double bond and the triple bond inside the molecule. They add to it whatever that. I will never trust eating that thing here, because you don't know what they have added to it. Now the same thing with the tomato. I can change the color to purple or green or whatever. Yes, I can. Did you see any fruits or veggies in different color? Yes. Look at the paprika, the big one. Generally, long time ago, we know only green. Now we have a yellow, we have a red. So what's happened there? They inject those with chemicals and then just put the whole thing inside. But we don't know. I tell my wife, don't bring me red or yellow stuff. I eat just the natural green paprika, the big one. Because I don't trust what they have added through their from the beginning when they plant the whole thing. You don't know what they have added. So, and sometimes this addition is not compatible with our bodies, and we get cancer out of this. Most of our cancer is related to our food, believe it or not. We don't know what's going on with the food itself. So, that's the case. So, if you see one time a tomato looking white or purple or yellow, don't be stunned. You know what's happening. They opened up one of those triple bonds. I don't know where. They opened up this molecule or this double bond and added bromine or added chlorine or added hydrogen, or added fluorine. Okay? So, now you have a color, different color from the original tomato color. Are you following me here? I want to make you, that's unsaturation. Those molecules are unsaturated, meaning they can take in extra molecules to them. They can open up their double and triple bond. And that's what's happened in the watermelon. Somebody, if you have 1 second, then you can Google somebody had Googled the violet or purple watermelon? Look at the image. And you can confirm. I was stunned when I saw the color, meaning they add to it whatever they add to it, and then the color will change, because you don't have the original watermelon color, the red one. And the same thing with the tomatoes. They can't change the color of it. So anyway, so somebody found that? You found the purple? You found it? You trust you'll eat that watermelon? I can't trust that. So because unless they tell me what chemicals they have added into it, then I will argue on this, and then I can eat it. But without knowing, the same thing with these carrots. That's the structure of the carrots, guys. Now, if you see one day the color of carrots different from whatever you see, that's the original color of carrots. But if you open up those double bonds by adding whatever, fluorine, bromine, and then you can get a white carrot. One day you can see a white carrot, or a purple carrot, or a violet carrot. I don't know what color. So depending what you add to the double bond. Okay, guys? So Somebody asked me, I think you have asked, long time when we started the beginning, what's the difference between conjugated and non-conjugated? Remember that? Okay, so that's here, that's the answer of your, we answered it at that time, but that's just the conclusion of the different arrangement of the double bond. If they are alternating double bond, single bond, double bond, single bond, double bond, single bond, like this one here, just alternating. If they are alternating, that's a conjugated. If they are not alternating, they are coming double bond, and then single, 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 and then double bond, and they are not, there is no system there. It's like this one here. Those we call it not alternating, or not conjugated, or non-conjugated, correct? But some of them, they just double bond all over the places. All over double places, double bond. That's additive or cumulated or additive double bonds. Those are the three types of settings of that double or triple bond. So I think we answered that a long time ago, I think, last week or so. But anyway, so that's the difference between them. Conjugated, always very important. That's alternating. The conjugated is meaning the double bond is not located in one, is moving, correct? And the additive, the cumulated one, the double bond is restricted because all of them, they have the double bond. They can't move nowhere. But the alternating, the good thing about alternating, they move around the molecule. And that's what get what? More stability. So the difference between those type are more stable organic compound. More stable organic compound. Organic hydrocarbon. So if somebody will ask why is conjugated bond is very stable, because the motion and migration of the double bond through the whole molecules. So the double bonds can migrate here, and so on, can migrate. Double bonds moving around the molecule itself. Are you following me here? And that makes more stability for the molecule. I'll stop here, guys, and I'll meet with you this coming Thursday. I hope we'll finish most of the stuff there. Thank you very much for listening.